Greetings. My name is Alfredo Pados and I will present my review on articles concerning greenhouse warming. The article I chose was entitled Nonlinear Climate Sensitivity and its Implication for Future Greenhouse Warming, conducted by Dr. Tobias Friedrichs and company. Dr. Friedrichs is a researcher and a professor at the International Pacific Research Center, University of Hawaii. Basically, this study is about the effect of carbon dioxide in Earth's atmosphere. But before we go into that research, let me show you first why studies like this have to be conducted.
So I don't believe that global warming is man-made. I think that is natural, and that it does fall into a climatical pattern.
Okay, it's just a kid, so let me go on.
I understand that carbon dioxide that man produces is 3% of what nature produces. How can small changes to our production of CO2 impact upon something as large as the Earth? It seems absurd.
Absurd. All right, a good question. Anyway, so just one or more of these climate change skeptics.
I think CO2 is actually beneficial for us. It's heating up the earth, it's producing vegetation, it's producing food. I don't see what all the drama is. It's only going up a slight amount, and yet we're going to change our whole economy.
I think CO2 is beneficial. I think I will call you climate enemy number one. Now let us go scientific and dive into a research that measures the effect of carbon dioxide to average Earth temperature. Oh, by the way, my background here is the sea surface temperature anomaly from January 1982 up to December 2017. I intend to finish this presentation when we reach 2017. I want to start with what is supposed to happen without carbon dioxide. That is, I will calculate Earth's temperature had it been without greenhouse gas. First assumption, the Earth absorbs some solar radiation, but all of it will be emitted back into the atmosphere. Absorbed radiation shall be equal to the solar constant, or S naught, multiplied by 1 minus the albedo multiplied by area. Albedo here is assumed to be 30% or zero point 0.3, while Earth receives 1,360 watts of solar radiation for every square meters. On the other hand, emitted radiation is the product of emissivity of Earth, which we assume to be a black body, multiplied by the Stefan Boltzmann constant, the surface area of a sphere on Earth, and Kelvin temperature raised to the fourth power. Now we equate both terms since they are equal and do some algebraic manipulations. Substituting its values, we arrive at 255 kelvins or negative 18 degree Celsius, which is the Earth's temperature without greenhouse gas. This is what Earth should have been, all ice. So, it seems our climate enemy number one has a point. Greenhouse gases, especially carbon dioxide, warms up the earth to a temperature enough for animals and plants to live. We have been measuring CO2 concentration in the atmosphere using different methods and different points in time. Our scientists can even go as far back as hundreds of thousands years ago. 400,000 years ago, for instance, it had risen and fallen, but never stayed higher than 280 molecules of CO2 per 1 million molecules of air until 1950, and now it is 405 parts per million. The question is that number high enough to cause us harm? To answer the question, we can calculate how sensitive Earth's climate system is with changes in CO2. This is called equilibrium climate sensitivity. Equilibrium climate sensitivity of Earth, or ECS, has been estimated several times before. It is usually expressed per doubling of CO2 concentrations. although their numbers are too high and very alarming. The most prominent of them was given by Professor Jules Charney at Massachusetts Institute of Technology in 1979. The number was 3 degrees Celsius with an uncertainty of plus minus 1.5. Thus, the lowest would be 1.5, which is okay, and the highest would be 4.5, which is disastrous. Of course, this was 1979. Computer models at that time are not that good, and data are not so vast. In the current study of Friedrich et al. In 2016, they used paleoclimate records at sea surface temperatures to model variations at 1,000-year resolution. They are so careful that they employed two methods: global surface air temperature reconstruction based on paleoproxy sea surface temperature, and global surface air temperature reconstruction based on paleomodel simulation. The first method calculates the average paleo sea surface temperature using 14 data points over the past 784,000 years. They first tested how reliable these data are in determining the global mean sea temperature variability. First, they used the simulation LOVCLIM, that stands for LOC, the code F-built Clio AGSM model, and then the LGM and PI simulations, or last glacial maximum and pre-industrial model. Both methods produced identical results, thus making the data points reliable and valid for calculating global mean sea surface temperature. Then they went on to calculate the global average sea surface temperature and converted this to global surface air temperature, which is where we are most interested with. For the second method, they use 63 paleo sea surface temperature data points across the globe from 140,000 to 10,000 years ago. They used the simulation LOVCLIM to reconstruct the surface air temperature from sea surface temperature. They then correlated these calculations, the calculations from the first method, which resulted to an R of 0.79, which we know is a strong correlation, which implies that the two methods agrees with the results. These are the locations of temperature readings used in their study. The 14 paleo sea surface temperature for the past 784,000 years and 63 paleo sea surface temperature from 140,000 to 10,000 years ago. They averaged results from these two methods and finally was able to come up with global mean surface air temperature, which is in agreement with the works of Hansen et al. In 2013, whose study used deep ocean temperatures extracted from oxygen isotope compilation. So far, so good. This study is now okay to go because of three things. Number one, it uses a data range from longer time periods. Number two, it agrees with other methods. And number three, it agrees with other studies using different methods. This figure shows global surface air temperature and radiative forcing anomalies for the last 784,000 years. At figure A, global mean surface air temperature anomalies in Kelvin reconstructed from 14 long-term paleoproxies of sea surface temperature in blue lines is shown. We can see that temperature rises and falls to some degrees. Now at figure B, the black line indicates global mean surface air temperature anomaly in Kelvin. The predictions here indicates alarming anomaly by the end of the 21st century. At figure D, Radiative forcing anomalies is shown from ancient times to present up to the future, where we see that radiative forcings will continue to increase. And then here, they compared CMIP 5 projections and their projection based on paleoclimate model, where we can see that the current model projects higher temperature rise. Temperature changes over the last 784,000 years is now reconstructed. Previous predictions, such as CMIP 5, showed that relative to pre-industrial age in 1880, global mean temperature by 2100 will increase at least 3.42 kelvins up to as much as 6.4 kelvins. On the other hand, this study by Friedrich et al., using ancient climate records and Love-Klim simulation, showed higher temperature increase of at least 4.78 kelvins to at most 7.36 kelvins. Of course, this prediction is only when the carbon dioxide concentration will reach the predicted value of 900 parts per million by that time. Thus, equilibrium climate sensitivity is a better number of temperature prediction. I must mention that before this study of Friedrich et al., methods used for calculating equilibrium climate sensitivity were obtained from either of the following: deep ocean temperature, conversion of oxygen isotope data, assumptions regarding polar amplification, and shorter paleo records or paleo time slices. Since this study in review have a vast 784,000 years of global climate records, they would have a more reliable result. Another important thing to note is that the calculation used in this study adjusted for corrections for possible sources of radiative forcings. Specifically, they explicitly considered changes in greenhouse gases, land ice, and aerosols, thus reducing sources of uncertainties. Finally, I now present the result. This is split into warm and cold regions, since several studies suggested that these regions behave differently. Results showed that in cold regions, temperature will rise by at least 1.52 kelvins to at most 2.04 kelvins when CO2 concentration doubles. In warmer regions, climate sensitivity is higher. On average, temperature will increase by 4.88 Kelvin when CO2 doubles, with an uncertainty of 4.29 Kelvin up to 5.44 kelvins. The only good thing about these numbers is their small uncertainties. Unlike from previous studies where the minimum climate sensitivity is far from the maximum value. That is the only good thing with these numbers. We can average warm and cold climate sensitivity to come up with a single number, 3.22 Kelvin per doubling. However, authors suggest otherwise since it underestimates warmer regions. Okay, this study suggested that without human-induced greenhouse gases such as CO2, temperature will rise and fall, but to some extent. With the contributions of humans, greenhouse warming will exceed those highest temperatures ever recorded for the previous thousands of years, and it will continue to rise as the amount of greenhouse gases are released in the atmosphere. Now we know, and now we have a concrete evidence that greenhouse warming is real. It is man-made, yes. Carbon dioxide is beneficial to some extent, but like always, we can't have too much at anything. We now know for sure that if it is business as usual, burning of fossils, our temperature will continue to rise. Now, it is all up to us. Hey, look! our 1999 records just broken in 2016.